Now, one of the things that we also have to mention whenever we look at these voltaic cells is we have a spontaneous process. And in each of these spontaneous processes, we have something called an oxidizing agent and a reducing agent. And we can define an oxidizing agent, or the function of an oxidizing agent is to allow another species to be oxidized. On the flip side, a reducing agent will allow another species to be reduced. Because as I kind of hinted at earlier, you cannot have oxidation occur without having a reduction reaction happen simultaneously. So we have to have simultaneous oxidation and reduction. So if we look at this particular problem, and if we have an oxidizing agent, it's allowing another species to be oxidized. So that particular species is being reduced. Some great oxidizing agents are transition metals in their highest oxidation state. These ones can be manganese 7+, like we talked about in the previous case. Another great one would be chromium 6+. So this dichromate ion, if you have chromium 6+ in a particular solution, it cannot be oxidized. It's going to be reduced. Okay? So in that case, Cr2O7 2- is an excellent oxidizing agent because it's allowing something else to become oxidized. That something else in this case is the iron. So the iron is going to be our reducing agent because iron solid is being oxidized to iron 2+, so it is facilitating some kind of reduction that's going to happen. All right? So if you have, and we can look at there's varying degrees of oxidizing and reducing agents. And we can look at the cell potential. Okay? Whatever makes the cell potential the most positive is going to be your best oxidizing/reducing agent. Because the more positive that is, the more spontaneous something will be. Okay? So we can compare and contrast oxidizing and reducing agents. One more thing that I will say here, and I need to mention this before I let you guys go today, is that these electrochemical, if you have an electrochemical process, it's going to proceed until it reaches equilibrium. So one of the things that we have to look at is that at equilibrium, we know that Q is equal to K. We know that delta G is going to be equal to 0. And that E cell is going to be equal to 0. So as these particular electrochemical reactions proceed forward, the concentrations of the reactants and the products are going to change as that reaction goes forward. For example, in this case, if we monitored the concentration of the dichromate versus the concentration of the iron, as this spontaneously moves forward, our dichromate concentration is going to drop and our iron concentration is going to increase. So the question is, how long can these reactions proceed? How do we maximize their cell potential? And at what cost would we want to maximize or minimize certain concentrations? Because by manipulating the concentration, we can manipulate what Q is going to be, and we can change our cell potential. So what we're going to look at on Wednesday is how can we manipulate concentrations in these particular cases to maximize our cell potential. because that E naught value that we're using indicates that all our concentrations start out at 1 molar. What happens if we start out with a 10 molar solution or a 5 molar solution? Why in a battery are they really, really acidic and we bump up that H plus concentration?